Last time we talked about recursively defined sets, and this time we're going to be learning about how to prove certain things about these recursively defined sets. We'll be doing that by using induction. So in this context, we would call this structural induction. That's the type of induction that will be used to prove theorems about these recursively defined sets. So first of all, we're going to see an example where we use structural induction to prove that any string of properly nested parentheses is balanced. So last time we did talk about that recursively defined set that was called properly nested parentheses. And so we're going to prove this time that they are balanced, but we need to first talk about what that means to be balanced and a little bit of terminology that we'll need to use. So first of all, we would say that a string of parentheses is balanced if the number of left parentheses is equal to the number of right parentheses. That's what we would guess that meant, probably, right? Okay, now in this case here we see this string of parentheses, and we've got just several parentheses there, and we can take a look at that and realize that that is what we would consider properly nested. So that would be an element in that properly nested parentheses set. And we see that the number of left parentheses and right parentheses is both 3. If we count the left parentheses, 1, 2, 3, and the right parentheses, 1, 2, 3. So the number of left parentheses and number of right parentheses are both 3, and so we would say that the string is balanced. So another little bit of terminology here. If X is a string of just left and right parentheses, then we're going to use this this notation left, and then in square brackets an element in that set, in a set, in the set that just is made up of left and right parentheses. So left and then whatever set is in there is equal to the number of left parentheses in X, and then right with that same square brackets and that set inside is the number of right parentheses. And I shouldn't say set inside, we're talking about the string. So in this case here, when we're talking about X, if I said set before, I meant to say it's a string. X represents some string, and then left X would be the number of left parentheses, right X is the number of right parentheses in this string of left and right parentheses. So let's look at this. Here we see this string of some left and right parentheses. Let's figure out what these what right of this is. Well, we would just count the number of right parentheses. So for that first one, we would say there's 3 of the right parentheses. In the next case here, we've got a string of parentheses, and we would add up how many left parentheses there are, since it says left, and we would have to say 0 there. In this next case here, we've got a string of parentheses, and we would count the number of left parentheses, and we would see 3. So here is our definition again of the set of properly nested parentheses. So look over there to the left here. We remember that we start with the basis of just this one little set of parentheses, and we say that that is in our set that we're going to call P. And then we say that anything that can be derived by using any combination of these rules below, rule 1 or 2, we would say then is also an element of that set that we're going to call P. And again, P is going to represent the set of properly nested parentheses. So if you remember, rule 1 was that if we start, well, first of all, before I talk about the individual rules, remember these recursive rules start with if U is in P, is an element of P, and V is an element of P. So we're starting with 2 strings of what we would consider properly nested parentheses. Then rule 1 says if we start with, let's just talk about U, which again is an element already known to be in P. If we put parentheses around it, a left parentheses on the left, a right parentheses on the right, rule 1 says that that also then would be an element of P, and it would be properly nested. Rule 2 says if we start with U and V both being properly nested, then if we put them together, just concatenate them with nothing in between, then that also is in P. So those were the rules in order that we would be able to use to come up with any, anything that could be created using these 2 rules, then we would say would be considered properly nested. So over here on the right, you see that now we want to show something. So we're going to try to prove something. It says show that for every properly nested set of parentheses, and that would be, if we're calling that set P, then every X in P, then X is balanced. And again, balanced means that the number of left parentheses equals the number of right parentheses. So that's what we want to prove, that that every string in X would be balanced. So first of all, we're using induction. So we need to show that, first of all, that the basis, whatever is we begin with in creating that set, show that that is balanced. So that's what we do first. So remember before when we were talking about mathematical induction, it was usually something that involved some numbers like n or k, that kind of thing. And so we said that proving the base case would be proving for when n is equal to 0 or n is equal to 1, whatever we want to start n with, right? So that's what we started for the base case. But here, for structural induction, we don't necessarily have numbers like k and k plus 1. We might, but we might not. And so the first step, that base case, would be showing that the basis, this element, that any elements that start out in P as part of the basis, showing that whatever we're trying to prove, this property we're trying to prove, is true for the basis. Okay, so for the first thing then, for mathematical induction, we would need to show that what starts out as the basis over there on the left, which is just that simple set of parentheses, we need to show that that's balanced as part of the base case. Okay, so and then we'll do that here in a minute, but just overall, we'll talk about overall and then we'll actually do it. So we would need to do that first. Then for the inductive step, we would need to show that for each rule that could be used, that if assuming, remember before for induction we said assuming that this is true for k, then we're going to prove that it's true for k plus 1. But again, here we don't necessarily have these numbers that we're calling n and k, and so what we would have to do for the inductive step is to show that to assume that there's a certain element is this is true for a certain element. So assume that it's a balanced string, and then show that if we use any of the rules for recursive rules to come up with a new element, we need to show that, assuming that it started out balanced, we need to show that whichever rule we would use, it would still, our new element by using one of those rules would also be balanced. Okay, so for case 1, we would need to say, let's assume that U is balanced, and that would be U, again, something that's already part of P, and then we would need to prove that U in parentheses is balanced. And remember, we get that by using Rule 1. So we would need to show that. And then for case 2, we would need to be, working with Rule 2. And we'll say, okay, well, again, we're going to assume, we're told that U and V are in P, so we know they're properly nested, but we're also going to assume that this property is true that we're trying to prove, which is that they are balanced. Both of them are balanced. So we'll assume that both of those are balanced, and then prove whatever we come up with by using Rule 2, which would just be U and V next to each other. We would need to prove that is also balanced. Okay, so that's kind of how we go about this. So now let's go ahead and prove this. So again, over on the right in the box, remember that's just the recursive definition for that set of properly nested parentheses. Remember, we start with the basis, and then we have 2 rules that we would use here in order to get new elements of that set. And then our theorem that we're trying to prove over here at the top left is if some string is in P, P being that set of properly nested parentheses, then that string X would be considered balanced. Left X is equal to right X. And we're going to prove that by induction. So first of all, we start with the base case. Look to see what the basis is, and we need to show that this property, the fact that it's balanced, is actually true for this basis set. So here, what's the basis set? Just that one little set of parentheses. So let's take a look. The number of left parentheses in that is equal to 1. The number of right parentheses is equal to 1. And so therefore, left of that string is equal to right of that string. So for that set, for that element that's in the set due to it being the basis element, that particular one, we have proven that it is balanced. Now we'll go and look at the inductive step. And we're going to have to split it up into 2 cases, as we've said, because we can get elements using either Rule 1 or Rule 2. So for case 1, we're going to assume that we started out with something that's, properly nested, and then we used this Rule 1 to get a new one. Okay, so we're going to, for case 1, we're going to assume that Rule 1 is the last rule applied to construct this new element X. Okay, so remember, if that's the case, if we used Rule 1, we would have started with something that was already in the set, P, and then put parentheses around it, because that's what Rule 1 says. We would have put parentheses around it, and we would then be assured that that is an element of P. So we need to know if we do that. And remember, for the inductive step, there's always 2 parts. There's the what do we assume, and what do we prove. So for this case, we need to assume, and for all cases really, but when we're doing structural induction, so let me just say that first, for all cases, what we do is we assume that what we started with did have this property, and then we use the recursive rule that we're looking at, and then try to prove that the new element would also have that property. Okay, so in this case here, we're saying that we know that U is in P already, and then we're going to put parentheses around it to construct a new element that we also know is in P. So what are we going to assume? We're going to assume that what we started with, which was the U, we're going to assume that's already balanced, that is balanced. And then we're going to prove that once we use this rule 1, that then our new element is also balanced. So we would need to prove that u in parentheses, because that's what we would get when we apply rule 1, that the left of that is equal to the right of that, or that is balanced. Okay, so we've got our assumption and we know what we need to prove. So since we know what we need to prove, remember that we'll start with the left part of what we want to prove, which is this part here. We'll start with that and see if we can get to this part on the right. Okay, so we start out with left of left of that string where we have u in the middle of a set of parentheses. What is that equal to? Well, we know that all we did when we went from u to this new element is that we put a set of parentheses around it. So we would have just added one left parentheses. So we know that this new element has one more left parentheses than u did to begin with. So we know that the left of this new element is equal to 1 plus the left of the original element. But remember, we're making this assumption that u was properly balanced. So I know for sure that, not I know for sure, but I'm assuming that the left of u is equal to the right of u. So I can replace left u with just the right u. So that's what I've done here. So just replace the left u with right u. And then, now let's take a look at what would be next. Well, what is 1 plus right u? Well, remember, by applying that rule 1, all we did was put one set of parentheses around it. So we do know that 1 plus the number of right parentheses in u is going to equal the number of parentheses in our new element, where we just put a set of parentheses around it. So now I've proven what I needed to prove, that the number of left parentheses in my new element is equal to the number of right parentheses in my new element. So that's for case 1, when we used rule 1 to come up with a new element. Now let's look at case 2. Case 2, remember, says we start with u and v both being properly nested, and then we put the two together, and then we know that they're also properly nested. But what we need to prove here is that that new element that we would get when we put u and v together would also be balanced. So for case 2, we're assuming that rule 2 is the last rule applied to construct x. And remember, we started with u and v in P, and then we would get a new element where we just put u and v together. So again, we're on the inductive step, and we have an assumption. So we need to assume something and prove something. Remember, by the way, this assumption is always called the inductive hypothesis. So what would be the inductive hypothesis again for this right here? Assuming that rule 2 was the last rule applied, then our assumption, our inductive hypothesis, is going to be that the original elements that we're starting with were already properly balanced, right? Because remember, that's what we're trying to prove that they are properly balanced. So we're going to assume that the number of left parentheses in u equals the number of right parentheses in u, and we're also going to assume same thing for v. And what do we want to prove? We want to prove that when we put the two together by applying rule 2, that the number of parentheses is the same between the left and right parentheses. Okay, so then we have uv in there. Okay, so again, let's start with what's over on the left of what we're trying to prove and see if we can come up with what's on the right. So first of all, starting with the left of this new element uv, number of left parentheses, well, if all we did was put u and v together, then the number of left parentheses in both of those, once they're together, would be the sum of the number of left parentheses in each one. So left UV is equal to left U plus left V. Okay, right? Because all we did was put them together, didn't change the number of left and right parentheses that were in there. But remember, our assumption is that U is balanced and V is balanced. So if that's the case, we can replace left of U and left of V with right of U and right of V. And then we can say, well, if I have, the number of right parentheses in U, number of right parentheses in V, if we put them together, then we would still have the same number of parentheses now, and we would just combine those, add those together. So the number of right parentheses in UV would be equal to what was right above it. Okay, but now we see that we've proven what we needed to prove, that the left of UV does equal the right of UV. So what we did, we started out showing it's true for the base case, for the basis of that set. Then, for however many rules there were, we needed to apply that inductive step, where we assume it's true for an original element and prove it's true once we use that rule to get a new element. So we did that for case 1, and then we also did that for case 2, and so therefore we would say that we have proven this theorem. Last time we also talked about perfect binary trees, and remember what that was all about. We talked about what a tree is. It's going to be, a tree has these different vertices and then these what we call edges that would be what we might consider the branches of the tree. And remember that the way we obtain a perfect binary tree is to start with a perfect binary tree, make a copy of it, an exact copy of it, and then put those two identical trees together under one vertex right above it. So we would have one vertex above it with two edges coming down, joining those two identical trees. And then that would also be considered a perfect binary tree. So if you look over on the right, we could call these T sub 1 would be just the very basis of these binary trees, which would just be one little vertex. And then we could come up with T2 by taking two copies of T1, putting them together under a vertex. And then we get T3 by taking two copies of T2, putting them together under one vertex. And then you see T4 even, we started out with two copies of T3, and then put them together under a vertex. Okay, so we'll be kind of looking at these and calling them T1, T2, T3, and so on here, just for this example here. So we're going to try to prove something about this. So let's see what the theorem says. This theorem says, let T be a perfect binary tree, then the number of vertices in T is 2 to the k minus 1 for some positive integer k. Okay, so we've got a perfect binary tree, and if we count up the number of vertices, we could always write it in terms of 2 to the k minus 1, where k is some positive integer. Okay, so now let's prove this. Now we do see a k here, so we might think, okay, I'm going to prove it's true for k, and then also assume it's true for k and prove it's true for k plus 1. That's the kind of thing we did, in previous lessons. But remember here, when we have these recursively defined sets, what we're doing instead is we're going to, as part of the inductive step, we're assuming whatever we're trying to prove is true for one element in the set, and then show that it's also true once we construct a new element from the set. Okay, so that's where we're going with this. So that just to let you know. Okay, so first of all, though, before we get into the inductive step, we need to talk about the base case, which would be proving that this is true for the basis. Now, what's the basis of these binary trees? That's what we start with, and that would be this T1 that just has one vertex. So we need to show that that this is true, that this, what we're trying to prove, is true for T1, T sub 1. Let's let V of T denote the number of vertices in T, in any tree. Okay, so if I have some tree inside this function V, we're saying that denotes the number of vertices. So let's look at the number of vertices in T1. Well, we go over and look at T1 and we just count, and there's just one. So V of T1 is equal to 1. Now, can we write 1 as 2 to the k minus 1, where k is some positive integer k? And we could just think about it a minute and think, yeah, I'll put a 1 up there for k. And so that would be 2 to the 1. That would be a 2 minus 1, which does equal 1. So we have shown that for the base case, for the basis here, this theorem appears to be true. So that's the first part. Now we go on to the inductive step. Here, unlike last time, there's not several different ways in order to come up with a new element. It's just always the same way. We take an identical copy of a tree, put it together with, put those two copies together, and we have a new element. So thinking about that, remember then, what would we be wanting to assume? What would we be wanting to prove? Well, we'd want to assume that a tree that we're starting with does have a number of vertices equal to 2 to the k minus 1 for some k, positive integer k, and then prove that assume that it's true for an existing perfect binary tree, and then show it would also be true when we come up with the new element, which would be taking those two trees and making taking the one tree, making a copy of it, and putting it together. Okay, so let's kind of come up with some terminology here. Let's say that T prime is the perfect binary tree that's created from any old tree called T. Okay, so over here, imagine that we have some tree there. I've just made a triangular shape because it could have as many levels as it could have all kinds of numbers of levels there. So we're just saying some generic tree T, and I'm going to make a new element from that. So I would take a copy of T and then put two edges that join a vertex at the top, and that would give me my new T prime, right? That's how I would create a new element in this set of perfect binary trees. So now that we have that that terminology where T is what we're starting out with, and then T prime is our new tree, then now we can kind of talk about this in terms of T and T prime. So what would we want to be assuming as part of this inductive step? The assumption would be the inductive hypothesis. Well, remember here for structural induction, we're assuming it's true for one element and then proving it's true for a new element that has been derived from that earlier element. Okay, so in this case, T is what I'm starting with, so I need to assume that this property that we're trying to prove is true for T, the tree that we're starting out with here. So we're assuming that the number of vertices in T is equal to 2 to the k minus 1 for some positive integer k. And then what would we need to prove? We would need to prove that also the number of vertices in T prime would also be 2 to some positive integer power minus 1. So we're just going to say here, let's just call it another positive integer. It's not going to be the same, we called it K for our assumption. So now for what we're proving, we're saying, okay, it's going to be 2 to the J minus 1 for some positive integer J. Now, we could still use it as, say, K, because in both cases, we're just saying it's some positive integer. But it could be a little confusing because somebody could say, well, wait, it's not that, K's aren't equal. So we're just going to make things a little simpler, we're just going to call it J over here. So that's what we would need to prove, that in our new tree, T prime, we also have that property of the number of vertices equaling that. Okay, so again, to prove this here, we'll start with what's on the left here. Start with that, and then let's think about what that is equal to, the number of vertices in our new T prime. Well, it's equal to, and this isn't completely done yet, we're going to add to this, but take a look at what I have here, 2 times the number of vertices in T. So remember, to get T prime, we took 2 copies of T. So yeah, all of the vertices in one T times 2 would give us, some of it, but then remember we had to combine those with one vertex at the top. So we would then add 1. Okay, so add the number of vertices in T, take that times 2, add 1, we get the number of vertices in T prime. Okay, now let's use our assumption. Remember, our assumption is that the vertices in T the number of vertices can be written as 2 to the K minus 1, where K is some positive integer. So I'll replace the V of T with 2 to the K minus 1, assuming K is some positive integer. Now we just have to try to see if we can get to this right here. So let's just do a little bit of algebra here. Let's distribute the 2 in. So I have 2 times 2 to the K, and then minus a 2. So just distributed that 2 in like that. Then I have that plus 1. Well, now let's write this term here as just a 2 to the K plus 1. And then minus 2 plus 1 is just equal to minus 1. Okay, now have we proven it? Well, if K is some positive integer, then K plus 1 is a positive integer. So we then have shown that the number of vertices in T prime is equal to 2 to some power that's a positive integer minus the 1. So, if we wanted to go on and talk about it in terms of J, then we could say, so I could write it as 2 to the J minus 1, where J is equal to K plus 1, which would have been, again, the number of vertices, the K for that previous one. And so, again, J would be positive integer. So, yes, we have proven that pattern. Okay, so we proved it for the base case. Then, since there was only one way to get a new element, we did the inductive step where we assumed it was true for any perfect binary tree T, and then showed that it was also true for T prime once we created that from our T. So we would say by induction, we have proven that this is true. There is an additional exercise here in this section that would be good for you to look at. There will be participation exercises, of course, for points. There are no challenge exercises associated with this section. So for some extra practice, it would be good to take a look at the end section, the additional exercises, and find number 2 and take a look at that and try to work it yourself. I do have the solutions open so you can take a look if you need some help, but that would give you some extra practice for this section.